The mathematics recognition problem. The mathematics recognition problem is to given some data to figure out what is the mathematics, the mathematical formula, equation, or equations that accurately or nearly accurately describe the data. The mathematics or the mathematical model enables us to understand the data and to make predictions, and in engineering applications to design machines and systems that will work correctly and do new things, important things that we need done. The mathematics recognition problem is not a new problem. It dates back to the earliest days of science and engineering. One of the earliest successes in recognizing the math, actually figuring out what governs a physical process, was projectile motion. It was figured out by Galileo Galilei in Renaissance Italy in about 1600. It's a very simple rule. If you stand on top of the Empire State Building and drop a ball, the distance it covers is exactly proportional to the square of the time. So in 1 second it will cover 16 feet. In 2 seconds it will cover 64 feet. There's a constant acceleration from the Earth. It's almost the same everywhere on Earth. And that acceleration is 32 feet per second in English units and 9.8 meters per second in metric units. It describes the motion of cannonballs, which is what Galileo was concerned with. He wanted to know how to point cannons to hit a target. This wasn't understood very well in Renaissance Italy, so people would actually point the cannons in quite the wrong directions. It also applies to modern activities like baseball, sports of various types, other activities today. It affects us all the time. We drop things, we jump up and down all the time. The projectile motion is very simple. As time has progressed, we've studied more complicated phenomena and collected more data and learned and developed more advanced mathematics, which is generally more complicated. The mathematics typically has more symbols in the expressions. This is the bell curve or the normal distribution. It's also called the Gaussian after Carl Friedrich Gauss. This often describes the distribution of seemingly random variables. For example, it's a pretty good model of the proportion of people who have a certain height in a certain population. So this is data from the U.S. Centers for Disease Control on the height distribution of adult men between the age of 20 and 29. And they have a distribution that's very close to the Gaussian or normal distribution, the bell curve. There's a single peak. The mean or average height of American men is, in this age group, is 69 inches. That's 5 foot 9 inches. It has a width, a so-called standard deviation, of 3 inches. What that means is only about 4% or so of men are higher in height than 6 foot 3 inches. And if you go out to 3 standard deviations, so that would actually be about 6 foot 6, it's something like 1 in a couple thousand, actually. And according to the Gaussian, it's extremely rare for people to be over 7 feet. Maybe 1 in a million or 1 in a few million people is expected to be over 7 feet. And of course, it's extremely rare to encounter people who are over 7 feet. As an application of this is relevant to running a basketball team and recruiting people to work for your basketball team. Basketball players tend to be very tall, and at least up to about 6 feet 7 inches, maybe even higher, feet confers a significant advantage in basketball. So basketball players, the NBA, the National Basketball Association, the average height of an NBA player is 6 foot 7 inches. Quite a number of them are over 7 feet tall. A high percentage of the people in the United States who are over 7 feet tall are in the NBA. Now, this is an example. If you're running a basketball team and you want to figure out how you can recruit the best potential basketball players, you have to look at more than height. It turns out the very best basketball players often aren't the very tallest. In fact, many of them are more like the 6 feet 7 inches or 6 foot 8 inches, typical of the NBA players. Other factors obviously come in, like weight, age, and probably a wide range of factors. So you need a multidimensional model to identify your best candidates for basketball players, not just the height, not this simple. The two examples I've given are sort of low-hanging fruit, things that were figured out a long time ago, where we have data that can be described easily by something like a polynomial, like the square of the time, or something like the Gaussian. These have been figured out. The problems that continue to plague us are these multidimensional problems, like trying to predict who would be the best candidate for playing basketball. That we don't fully understand. Many of the problems that now are difficult or are stumping us involve multidimensional data where you don't have a single data point like height, you have a whole series of factors. The weather is a common and well-known example of this, very important. This is a picture of Harvey hurricane, the Hurricane Harvey, which caused $125 billion in damage and killed about 68 people in 2017. A dramatic example of how important the weather can be to us. The weather involves variables which have values at every point in the atmosphere, and they include things like the position of that point, the height, the altitude, the longitude and latitude, the north, south, east, west position of that point, the pressure of air at that point, the density of air at that point, the temperature of the air, the humidity in the air. If there are water droplets, it's not just how much water, but the size of the water droplets. Are they small? Are they big? They are typically big in a storm where it rains. Quite a number of factors. The velocity of the wind is different at every point, and it can vary quite a lot. In a hurricane, it's a vortex. It's whirling around, and there's all sorts of turbulent motion taking place, so it's very complicated. So multidimensional problems are difficult. They're difficult for human beings to visualize and think about. Even something like the weather, that's an everyday thing, because there's so many of these factors, the dust in the air and water droplets and temperature and other things, it's actually difficult even for human beings even to visualize and think about the weather. And it gets much worse as we get to more complex problems. So for example, this is the blood coagulation system. The blood coagulation system is very important. So this is what decides whether your blood clots or not. If you get a cut, it's very important that the blood clots and forms a scab, otherwise you'll bleed to death. On the other hand, it can make mistakes and clot incorrectly in the heart, which causes heart attacks, or elsewhere in the body, which causes strokes. 633,000 people died of heart attacks in 2016. Almost all of those are attributed to blood clots. Similarly, about 140,000 people died in 2016 from strokes, again, usually attributed to blood clots. The problem is the blood coagulation system is very complex. It's governed by at least 30 blood clotting factors which perform some kind of complicated computation to decide whether to clot or not to clot. It's interconnected in ways that are not fully understood with your digestion, with your pain system, with how you feel pain. It's quite complex and poorly understood, and many results from studying it are confusing. So for example, some studies of some populations will show that a high-fat diet is bad for you, that it causes or seems to be associated with high rates of heart attacks and blood clotting improperly, particularly as people get older. On the other hand, populations in the Mediterranean that actually have high-fat diets, people in Italy, Italian-American populations in the United States, actually have low heart attack rates relative to comparable populations of Americans, people who don't eat Italian or Mediterranean-style food. Now, there are complicated attempts to explain this kind of contradiction. The underlying problem is we don't understand the system very well. We don't know how what you eat impacts how this system works. We don't know how it interacts with other parts of the body. Consequently, we can't predict what the effects of changing your diet are, what the effects of drugs are. We have great difficulty in figuring out how to design and develop drugs or systems of drugs that might reduce or eliminate heart attacks and strokes. If we had a quantitative model, if we could recognize the probably complex math behind the blood coagulation system and its interactions with many other parts of the body, with the digestive system, then we could predict precisely in a scientific engineering way what you should do, what you should eat, what exercise you should do, all these kinds of things. So that understanding is not here. It is so high in dimensionality that human beings can't visualize very well what's going on. We can't think about it very well. So it's difficult for us to look at what data we have and understand what's happening, right? We just can't look at all these complex variables and see the pattern. So we've picked the low-hanging fruit, the things like the Gaussian and height distributions. We are left with these complex problems which are frequently multidimensional. Even if they're one-dimensional, they're very complex, and in some sense they can be converted into multidimensional problems. This makes them very hard for human beings to think about, and the recognition of the mathematical formula is largely a human activity. We look at data, we look at graphs from the data, we look at scatter plots, and we say, what does that look like? When you're up in 30 dimensions, you can't recognize it. A human being cannot visualize 30 dimensions, and we have no way to display the 30 dimensions, really. I mean, you can have a table of numbers, but there's no real way to see what's going on. On the positive side, we have an explosion of known math. There are thousands of math journals. We know far more math than Galileo knew, far more math than was known by Gauss. So in principle, we may actually know the mathematics to describe the blood coagulation system or other high-dimensional systems. We may actually know pretty much what's going on in weather, but we can't connect that mathematics to the data that we have and develop an accurate model or adequately accurate model. Now, fortunately, computers have the capacity to both understand the math. So in fact, most of this math we now know is in a computer readable form. So most of these journals actually use typesetting systems like TeX and LaTeX to represent the mathematical formulas. So the vast majority of the published math in the world today is in these typesetting languages, which are at least readable and understandable by a computer. Also, and even more importantly, much of the math has been converted into scientific programming languages, mathematical programming languages like Python, the R statistical programming language, MATLAB, and a few others. So they're actually an executable format already where computers can go out and actually execute these formulas, actually model them. All of this information is available. It's far more than one individual, even a Gauss or a Galileo, could know. It's far more probably than a team of hundreds of such people could know. It is, however, in a format where we can import it into databases in computers, and a computer can actually know all of this math, far more than a human being knows. And computers, unlike human beings, can operate in higher dimensions. They can represent 30 dimensions or 500 dimensions as multidimensional arrays in memory, and they can actually do pattern recognition, computer vision operations in these high dimensional spaces and recognize that this data is this math in this giant database. And so this is the crux of the math recognition sort of solution, how we can go beyond what we are doing now, which is with human beings often having to do a lot of trial and error and often being unable to figure out what these high-dimensional, very complex problems or data sets actually are. So a math recognizer would have a comprehensive mathematical database of functions, systems of equations, and differential equations. This is the information that could be read in from Python, from R, from typesetting languages like TeX and LaTeX, from mathematical journals, giving you a comprehensive database of all the math known to people. The really hard part isn't actually reading in the math that we already know that's already in computer form. That's actually doable with current technology. The hard part is an algorithm or collection of algorithms which can search through that math and match it to a data set. So it would be like a Google search, except instead of for text, you give it some data, and this program then goes through this comprehensive database of math and says, oh, this is actually this formula, it's this function, it's this system of differential equations, here's the answer, and we're done. That's the hard part. That's what we're actually working on here at Mathematical Software. And it is under development. We certainly haven't cracked the problem completely, although we have some good prototypes with simpler problems like one-dimensional problems. We're working on the multi-dimensional problem right now. What we are looking for and how we can actually help you is if you have unexplained data. What we really want to find is unexplained data, important problems where traditional methods have failed. A human being sitting there with MATLAB or Python or something, doing two-dimensional plots or scatter plots or surface plots, the usual stuff, trying the math that they happen to know, trying to go through a library at their university or somewhere or Wikipedia to try to figure it out. It's not getting there, right? That's a problem we're looking for. Once I can prove out these algorithms, can help us develop the algorithms so that they work on real-world problems, focus our development of the algorithms and technology on important problems like blood coagulation so we don't go off the rails and spend a huge amount of time developing the ability to recognize some abstract topology math or some other mathematics that's really not relevant to real-world problems. We want to focus on practical applications. So if you have unexplained data, give me a call. We can see if we can work something out, and again, if it's an unsolved problem, we may have the solution for you. I'm John McGowan, and I'm the CEO and founder of Mathematical Software, and I can be reached by email at ceo@mathematical-software.com.